It turns out that most water systems in the United States have PFAS in them. But fish are great PFAS filters. As they swim through the water, they're absorbing PFAS. And what happens when you eat the fish? You eat the filter. You eat the thing that's accumulated the PFAS. So I've read multiple times that eating one freshwater fish in the United States is equivalent to drinking a year of tap water in PFAS accumulation. How does that make you feel? So we were talking last time about flash graphene, and I hope you noticed how you can really quickly make flash graphene. You can take any carbon substance and flash it, and in an instant make graphene from any sort of trash. And so now what we were talking about is that you can take any human waste, and we talked about food. Food is a particularly bad human waste because it forms methane when it decomposes as well. And then there's plastic waste and rubber tires and all the different plastics. We said you could take all of these different plastics and you could equally flash them, or you just take them all mixed together. And this really solves the problem of the human separation problem for all the different types of plastics. So remember, every time you throw some plastic out, humans are there separating them to try to do recycling. And recycling really does not work well. And I know everybody says recycle, recycle. Recycled plastic just doesn't work well, and you can tell by the price. You can't get below the price of the virgin plastic. So there are companies that take plastic waste and just heat it up. And they get light oils, medium oils, they get some monomers, and they try to use the basic chemicals that make up all of these polymers. But they always are left with a char, some unusable char. We can take that unusable char and flash it, turn it into graphene. If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus. So one of the sources we can use are rubber tires. And remember I told you these rubber tires are a big problem. They do treat rubber tires, and they can bring them back. They can thermalize them, and they bring them back to the carbon black, because about 30% of the weight of your tire in your car is carbon black. It's just a carbon sooty material that's made by the pyrolysis of methane. And you can take that carbon black and you put it in the rubber, and if that were not in the rubber tire would stretch too much. This really toughens the tire, that carbon black. It can be 30, even 40% of the rubber tire could be carbon black by weight. I don't know if you've ever picked up a new tire. Your hands are going to be black. And that's the carbon black that's all over the surface, because it's all inside it too. And that's why new tires will always make your hands black. It's carbon black. So what upcycling of plastic waste using flash graphene, here are some of the advantages. It's about $35 per ton of plastic that you have to put electricity in. If you're dealing with a different type of carbons, like something that's much higher in carbon content, like say a coal or petroleum coke, then it's about $30 a ton. Plastic, you have to put a little more energy, but that's not much. $35 per ton in electricity. No sorting, no pre-washing. Remember, the plastic has to be extensively pre-washed if you're going to use another method. But here, all the wastes in there, you just flash it. Everything goes in there. You don't have to worry about plasticizers, dyes, adhesives, food waste. There's no solvent, no subsequent purification. So this is a great way to make stuff. So in Europe right now, when a vehicle is retired, meaning that you had your primary purchaser of the vehicle, and then at the end of the vehicle, then they used it, say, for 100,000 miles, they sold it to somebody else, and they sold it to somebody else, and after that, what do you do with it? Well, now in Europe, that car comes back to the manufacturer. And they're like, you deal with it. And you're only allowed to bury 5% of the car, 5% of the weight of the car. So what do you do with all of that? Well, the metals you can melt down and recycle, because metals theoretically are infinitely recyclable. But what do you do with all the plastic? Because there's 200 to 350 kilograms of plastic per vehicle. And that includes all the seat cushions, all the underhood insulation, and all the cabling, all the plastic over the cabling, all the dashboard. It's all made out of plastic. So they didn't know what to do with this. So we were working with Ford. We had Ford send us 10 pounds of waste plastic that comes from a stripper lot. And a stripper lot is where they strip every wire, they strip everything, and you get all of these pieces off. And then what you do is they sent that to us, so it's all mixed up and it's dirty, and we flashed it and we turned it into graphene. And then we sent it to Ford Detroit. And Ford Detroit put it in their plastic composites, because ever since February 2020, all Fords have had graphene in it, underhood insulation and in the foam cushion seats. And so, for example, you can see here how here's a foam cushion for the seats, and you see it's a little bit darkened. That's because of the graphene content versus the one that doesn't have any graphene in it. And it did everything that it's supposed to do, meaning that it absorbs more sound by having the graphene in there. It increases the Young's modulus, which is the stiffness of the material, and the stiffness of this material, the toughness of it as well, and the compression force it increased. So it did everything that it was supposed to do. But the graphene was made from a former car's plastic. So what did we do? We asked them to send us I said, go ahead, send me these composites. So we got that actual composite. And guess what we did with that composite? Flashed it. So that's the big idea about all of this, is you can recycle it all the way around again and again. Aluminum boils at about 2600 centigrade, silicon around the same temperature. Carbon doesn't boil until about 4400, and so 4200, somewhere in there. So you can distill out all of those other heteroatoms, many of the other heteroatoms. Now, there are some things that wouldn't come out, but most of what you would ever find in plastic is going to come out. So it's self-purifying in that flash process. It's an amazing process. I mean, there's very few things like that. Oh yeah, so all of that, in the lab, that just goes out the fume hood. But in industry, you don't do that. All of these effluents have to be trapped. Yeah, and the metals aren't going to get very far. When their boiling point is up at 2500 centigrade, they're going to deposit on the first cool surface they see. It's never going to make it even out of the factory. So you're going to have something in there to absorb all of that. Yeah. Yeah. And now CO2, generally you let loose, and you're allowed to let loose a certain amount of carbon monoxide, but yeah, those have to be scrubbed. Yeah. So you have to check your effluent coming out industrially. Not in a typical research lab, because the amount that we evolve is just so little. It would cost you more to try to trap what we put out in an academic lab than it would be that you would catch, because there's a cost in putting filters in there. All right, so flash Joule heating. So what you're going to see is you're going to see all the different things you can do when you discover something in this world of nanotechnology. What you have to do is you have to try many different things and explore the scope of what you can do here. And so one of the things we did is we intentionally put in heteroatoms, and we just didn't heat it as high. And you can keep some of these heteroatoms in there. So you can see how we put in there these other heteroatoms. And so, so for example, if we put in nitrogen, you could have nitrogen at locations like this, and you can see that nitrogen in the XPS. So you can see those nitrogen atoms in the XPS. Good. And we can see those. And then what we could do is we can put on boron, we can put in nitrogen, oxygen, fluorine, fluorinate the surface, sulfur. We could mix them. We could put boron, nitrogen, or boron, nitrogen, sulfur. So you can put in different elements either on top of this lattice, above and below, or in the plane of the lattice, depending on the atom. Because fluorine can only bind to one thing, it goes above and below the plane. Oxygen can bind to two, so that could be in the plane. Then what happens is you can disperse it much better, because now it's got some heterogeneity to it. The more highly crystalline something is, the harder it is to dissolve. But when it has heterogeneity, then it dissolves easier. So these disperse easier in solution. So you test all these things. And then we used it as a catalyst, because the graphene itself can be a catalyst, but if you have heteroatoms there, the catalytic behavior can really go up. And so we use this for an oxygen reduction reaction, taking oxygen and reducing it. We used it in batteries. So again, we've used these films, and we grow the lithium on top of this for a lithium metal battery. We grow it on this, and it is better than just growing it on graphene, because these little heteroatom sites serve as an anchor for keeping the lithium on there. And so you try it with many different things to show the utility. You try a few different things, and then you write these patents, and you claim all around these things. So you file patents on graphene. Now you file other patents on heteroatom substituted graphene. And then you put claims in there, okay, when you're using this heteroatom substituted graphene in a battery, and then in a lithium ion battery, in a lithium metal battery. And so you put one claim after another, and you start, coming in and claiming territory on this new continent that you just discovered. And that way, if anybody uses it, they have to pay you. That's the reason you spend all this money and this time writing the patents. But this is something that several of you are going to actually end up doing in your lives, where you're going to have to think about the patent work on this. Okay, so here's where we scaled this up. So we did it on a larger scale. So remember, the laser-induced graphene is in microseconds, just growing on a surface, which we first learned about in CVD method for growing monolayer, takes seconds to hours. This flash joule heating is in milliseconds to a second in this domain. So it's showing you the different domains of time where you're applying this. Okay, and so we have all of these different sources, and we have different ways, and you can make carbon nanotubes from this as well. If you put in, say, an iron catalyst in with that carbon feedstock, that's going to nucleate and add and act as that growth for the carbon nanotubes. And we've talked a little bit about this before, but we'll see another picture of it. But here's different sources that can go into making this, and then there's different applications that we can use this in. So what we'll see is a few different applications. Here's how you test concrete. You make these blocks, and then you go over to Ryan building, and they have these crushing concrete. And so that's our building where we go to do civil engineering studies. And so you want to see how strong is that concrete. And so you have these systems that can crush concrete, and you're measuring how strong is this concrete in the sense of a compressive strength. And you can see when you're adding in material here, so you 0% addition to 0.1 weight percent addition, you can see that there's an increase in the compressive strength on an additive loading. So you get about a 35% increase in the compressive strength by adding tire carbon black turbostratic flash graphene, meaning you can take waste rubber tires, the carbon black that comes out of waste rubber tires, and you can apply that, you can turn it into graphene, which is turbostratic, remember has no ordering of the layers, and then you apply that to the concrete. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. All right, so shredded rubber tires can be turned into high quality flash graphene, and then this can be dispersed in solvents better and can enhance concrete. And so one of the other things we did is years ago, what we had done is we took, remember the CVD growth? We said that we could grow graphene just on a copper surface in a CVD chamber. we had put carbon nanotubes on there and grown the graphene, and we got a melding of the nanotubes to the graphene. Well, we did something similar where we put carbon nanotubes in here as our source. And then when we flash it, you can see where the carbon nanotubes, but you can see where some of the carbon nanotubes have turned into graphene. So you have this melding of graphene and carbon nanotubes. So it gives you an enhanced material. So you're taking two different nanomaterials and growing them now together and hooking them together. And the temperatures are high enough where you get this carbon-carbon fusing together. And so you can see these regions where you have these strings of graphene, these strings of nanotubes, and then these graphene domains between them. And so you can see this by TEM. You can see areas where you have nanotubes. You can see areas where you have graphene. And so they're kind of mixed together. And so this is what you see here. Here you see some nanotubes, and then you see graphene going between them. This graphene and the nanotubes fusing in with the graphene. Again, you can see this. It's suggesting covalent bonding. Here you can see carbon nanotubes going into these sheets of graphene. Here's a carbon nanotube, and it seems to just disappear into this sheet of graphene. So that says that the two are melded together. And then you can see what was, if you hybridized materials. So this is putting it in epoxies, and you can see what happens when you add more of these to it. The hardness increases. So this is where you just have the epoxy. So this is the hardness in red. In blue is the Young's modulus. Now when you start adding in some of this material, you can see these numbers start going up. And so you can get, about double on the hardness, and you go up, I don't know, 50% or something on the modulus, the stiffness of the material. And so you see how you can improve materials. And materials become really important. I mean, from the composites on your teeth, you get an artificial tooth put in, you get a composite, you get a filling. You want that thing to last, right? What if you got new teeth put in, and then you go home and the first dinner you had, the tooth is gone? You say, well, you never cared about materials. Why do you care about them now? Well, because my tooth fell out. And that's how important materials are. And you're driving down the road and your tires fall off your car. You'd be really concerned about materials properties. You sit on a chair and the chair just kind of crushes, and you'd be like, a cheap chair? I mean, that's a material. That's a cheap material. So when you have cheap materials, then you really notice it. If you have good materials, you don't notice the importance of materials. When you have bad materials, you really notice it and you complain a lot. We've also used it to reduce friction. So what happens if we can take these sheets and we can mix them in with different lubricants? So in this case, this was just polyalpha olefin 9, a typical lubricant. And what you can see is the coefficient of friction reducing as you add this in. This is huge. I mean, to you, lubricants, who cares? But lubricants in your car are so important, because if you can reduce friction, that's better mileage. And yes?
How does that compare to just graphite?
Yeah, it's better than graphite. We might have some comparison to graphite. But what happens with graphite is graphite shears down into thinner and thinner layers, but it's very hard to get it down into just 1 or 2 or 3 layers. And so the graphite is always going to be much thicker. You get down to a size that's called a graphite nanoplatelet. And then these get much thinner. And so you can see this reducing in the roughness. And so what you can study is what is the degradation to these steel balls over time. And you do these AFM studies, and you study how those have been deformed. I don't have it in here, but you study how those have been deformed. And you can see, you look at the amount of wear that's taken place, the amount of deformations that you see using these nanometer scale instruments. And you can see the reduction in this, because it's these little nanometer scale increments that you study that end up being big problems over time. So for example, when I was in high school, if you had a car that went 100,000 miles, you thought, wow, I got really a good lifetime out of this car. Well, now, if you have a car that kind of dies out at 100,000 miles, where where the pistons don't hold pressure anymore. You're like, I mean, this cheap piece of junk. I mean, what's going on here? Because you can get a couple 100,000 miles out of an engine all the time. In other words, the pistons, you're not wearing down. And that's because of tolerances that they've gotten and better materials properties and laser cut tolerances. And by doing that, you have much longer lifetime on engines. So all of these materials properties are enormous. The materials business is a huge business because this is the world in which we interact. We don't interact a lot with liquids. I mean, you're not sitting on liquids here, right? You're not walking around on liquids. We mostly interact with hard materials. And everything we interact with, from our clothing, you know, you buy cheap clothing and it falls apart. You buy quality clothing, it stays together better. And all of this has to do with all materials properties. So one of the things we wanted to do with concrete, so remember we said the concrete is 8% of all CO2 emissions of humans come from the concrete. So here's the components of concrete. You have air going into this. You have this cement. You have this water, and then you have the aggregate. So all this together will allow you to form concrete. Concrete takes cement, which is sort of like the glue of concrete. Cement is the glue part. Concrete is this whole composite of cement and what's going to end up as rocks, these aggregates. And so you mix a lot of rocks. So the aggregates will be 60 to 75% is going to be rocks in your concrete. And it's going to be 7 to 15% cement. You're going to add water to it. Some of this water is going to end up, the cross-linkers in there, and other of it is going to evaporate. But a lot of energy goes into making this. So the idea can we lessen this CO2 emissions, and can we use something, namely carbon, instead of rocks? Because it turns out that sand is one of the hardest things to get for concrete. You'd be like, sand? Come on, you can't be serious. Just go to the beach, you get all the sand you want. It turns out that not all sand is the same. So for example, Saudi Arabia has a lot of sand, right? You see these pictures. They bring in barges of sand to make concrete. You say, well, why don't you just use your own sand? Because they can't use the same sand. You can't use desert sand to make concrete. And so sand is a resource we're running low on, because concrete is the biggest building material known by far, way bigger than everything. We saw some of those numbers last time. So there's just so much concrete that's made all over the world as the world builds. Well, where do you get all that sand? So sand is becoming harder and harder to get. So could we replace it? And could we replace it with carbon? Well, why carbon? Because if we're going to bring up assets from under the ground, can we take that, rather than turning it into CO2? Remember I showed you this process last time where you could take methane, you pull the hydrogens off, you get carbon. And then could you take that carbon and do something with it? Because if you just throw it out, plants will end up taking it up, the plants die, and they'll form CO2 when they die. So it's going to end up in the CO2 atmosphere anyway, maybe just a couple of years later. It's going to end up in the CO2 atmosphere anyway. But can you take that carbon, kind of fix it for a long period of time? You don't have to fix it forever. If you just fix it for 100 years, you're good to go. Because in 100 years, we'll have different sources of energy, so we won't have to worry about CO2 as a problem. Now, we always want to be making some CO2. The world needs CO2. We need CO2 to grow all our plants and everything. But if you wanted to reduce CO2, how could you fix some of this carbon? And so the idea was, could you use this carbon in place of the aggregate? Remember that you had like 65%, 60 to 75% of concrete was rocks. Could you replace the rocks with carbon? Now, carbon's relatively soft. But what this student did is a very, very ingenious idea. He took flash graphene aggregate. So we get these chunks of metallurgical coke. Metallurgical coke, like baseball-sized chunks, come from this. And that is just, this is a U.S. coal product. It's a product of coal. and they just heat it up to, I don't know, like 400 degrees or something, and a lot of the oils kind of distill out, and it gets this particle. Now, if you just break this up and try to put it in concrete, it doesn't strengthen it at all. It's too soft. But what he did is he took those big things and he ground them up to different sizes to match the sizes of natural aggregate. So natural aggregate has little pieces of sand. Natural aggregate has little rocks, medium-sized rocks, and big rocks in it. All right, so there's all these different sizes. So what he did is he analyzed this. He says, okay, how much of it is sand? How much of it is 1 millimeter diameter rocks, 2 millimeter? And then he ground up his flash graphene into those same size patterns. All right, so you can sieve it out. You have sieves. This is not, and this is something you can easily automate, but he was just using these hand sieves. And then he put it in the concrete, made concrete out of it instead of using natural aggregate. He made concrete out of it. So this concrete has no rocks in it. It only has flash graphene of the same size as natural aggregate. And it's 25% lighter. You know, no surprise. I mean, carbon is, if you look on a periodic table, carbon's near the top. And if you start putting in iron, calcium, silicon, all of those are going to weigh more than carbon. So this ends up being 25% lighter. So you have 25% lighter material. But now, if that concrete doesn't work, if it falls apart, it's not any good, right? So you want to test this and test the properties. So when you went to test the properties, you look at these stress-strain curves, and you look at this at different ratios. What it comes out to be, he was able to totally replace the natural aggregate by flash graphene aggregate of similar sizes. It's 25% lighter, but you get 32, 33, and 23% increase in toughness, peak strain, and specific compressive strength, respectively. There was 11% decrease in the Young's modulus, the stiffness of the material. But this is going to have many applications, and you could probably bring this back up so you're not getting a decrease if you put more research into it. But he worked on this for, I don't know, 6 or 8 months, and that's what he got. So this is really encouraging that you can now use carbon, which you're trying to get rid of anyway. So rather than blowing it out into the air, you put it into the concrete. And this is going to stay locked up there for a long time. And that shows you what you can do when you come up with something that's new. Now you can start applying it into all of these different things. And every one of these things that I'm showing you is a business, a big business. All right, so remember what we can do is we can put any carbon source between 2 electrodes, flash it, we can turn it into graphene, or if we add a little bit of iron, say 1 weight% iron, as say iron chloride into this, when you flash it, that iron acts as a nucleus on which the nanotubes grow. Remember, the nanotubes, you get this carbon, it covers the metal particle, and then that grows a nanotube. And so you get nanotubes coming out of this. And so that's gone into this company, Universal Matter, which we talked about last time. Now, the graphene market is about 14 tons a day. About $400 million a year is the graphene market. Now, that market is going to go way up as the price of graphene comes down. When you can start pulling the price of graphene down low enough to start going into concrete, then you're going to have a much bigger market for this. Now, the nanotube market is about $15 billion a year, a much bigger market. Most of this is made in China. But I think we've got a great way to make these nanotubes much cheaper than anybody else. And so we can really drive the price down and start getting into these new markets. But when you want to do something, you got there's a lot here that you can apply. So PFAS is a totally unnatural compound. Human beings have made it. And I can guarantee you that you have PFAS in your body. How can I guarantee that? Because they've checked people. They randomly checked 3,000 people, and every one of those 3,000 people had PFAS in their body. You all have PFAS in your body. So what is PFAS? That is per and polyfluorinated alkyl substances, where you have a long chain with fluorine atoms on it. Instead of hydrogens coming off each of these carbons, you have 2 fluorines. At the end, 3 fluorines. And then may have some group on the end. Here's a sulfonic acid, here's a carboxylic acid, here's a sulfonamide. And so these ones with highly polar groups on the end would be water soluble. The ones, Teflon, for example, is not water soluble. That's a PFAS. That's polytetrafluoroethylene. Your whole life you've been cooking on Teflon surfaces. Guess what you've been eating? Teflon. And what happens is it goes into your body, and it turns out it doesn't come out. It just kind of stays there, just lodges in your lipids and stays there. And then also PFAS, these sprays that they put on carpets to keep them from staining, the sprays that they put on clothing to keep them from staining. You spray it on couches. You know, this spray that you could put on protects your couches, because if you spill oil on, say, a polyester, it just stains really badly. But if you've got PFAS on it, you can spill stuff and it just wipes right off. You spill water and just kind of beads up and runs right off. If you've ever seen firefighter foam, you know, firefighters will drive up in a truck and spray all this foam. Well, what is that foam? I don't know. It's foam. Well, that is PFAS in the water. There are over now 12,000 different types of PFAS that have been made. Different structures of PFAS, 12,000 different types. And so they're ubiquitous, they're all around us. They're in women's breast milk, they're in fetuses, they're in everything. And they're all through our environment. So it turns out that they're also in our water systems. So we're drinking PFAS all the time. So this has gotten into our water systems. They don't degrade easily at all, because nature sees this and like, I don't know what to do with a perfluorinated organic compound. I've never seen this before. So they don't degrade. So they just sit in our water systems. Now, how many people in here, I took a show of hands one time, how many people like fishing? Okay, so if you this is going to bother you a lot, but anyway, somebody's going to have to tell you. So if we drink water, there's PFAS in that water. It turns out that most water systems in the United States have PFAS in them. But fish are great PFAS filters. As they swim through the water, they're absorbing PFAS. And what happens when you eat the fish? You eat the filter. You eat the thing that's accumulated the PFAS. So I've read multiple times that eating one freshwater fish in the United States is equivalent to drinking a year of tap water in PFAS accumulation. How does that make you feel? But there are a number of effects now that are being attributed to PFAS. It affects your immune system, affects your liver, affects your kidneys. You can look through this list. If you just Google PFAS and the indications that happen because of PFAS, you can attribute every problem you have in your life to PFAS. Just attribute it to PFAS. I mean, you won't go wrong. So all sorts of problems are being attributed to PFAS. Now, I don't want you to become paranoid about this, but it's just a part of life. All right. And when I was a boy, they didn't have Teflon. All right. There was no Teflon in cookware. I mean, we used cast iron stuff. But when I was, I don't know, a young teen or something, they started talking about Teflon. Oh, this great Teflon coating. And they'd show the eggs just slipping out of the pan. And you'd like, hey, I got to get that. And who knew, right? Who knew? And so if you have Teflon pots and pans, just make sure it doesn't have, cuts and gouges in it that big chunks can come off. But anyway, next time you buy a set of cookingware, buy the ones that don't have Teflon, because actually they're phasing it all out. But firefighter foams, firefighters practice all the time at airports and everything. And so they light a fire and they spray it with this foam, AFFF, and it's like, I don't know, 6 different PFASs in there. We just got some samples of it. They're all phasing that out. And so it's going to be a big problem when you can't use foam and you got to go back to using water or some other dry chemical because it's worked so well. But anyway, that all would go into the ground and it would leach out in the ground and it would go into the water systems and end up in lakes and rivers, and that's where it comes from. Mainly it has been firefighters' foam that you really pour a lot into the environment. Yes, you can spray couches and carpets and stuff, but that's not running into the environment massively. It's been those foams That's really the massive introduction to the environment. Well, so you can use a carbon filter. So if you use a granulated activated carbon, that is pretty good at sopping up a lot of these polar, these aqueous soluble PFASs, all right? So these will get sopped up on this. So if you use a carbon filter, they're pretty good. They'll get a lot of that out. But now that it's on there, what do you do with that carbon that now has PFAS on it? Now, by weight, it might only be 1% PFAS by the time you're throwing out your filter and replacing it. Not even 1% by weight PFAS, but let's just say 1%. What do you do with that? The Department of Defense, who has a lot of PFAS problem, is no longer allowed to incinerate that carbon, because what they found is that when you incinerate it, these things break up, but you get small fluorocarbons like CF4 or C2F6. And those will then are more toxic than the PFAS that it started as, because now it's in the vapor phase. And so you're inhaling this stuff. So it's really bad. So the toxicity is really high. And so what do you do with it? Well, we've shown that we can take the PFAS that's adsorbed on carbon, we put it in a sealed system, so there's double O-ring seals. We apply a voltage and a high current, high voltage, and it turns into graphene. And we add into this calcium hydroxide or sodium hydroxide. If you add in calcium hydroxide, when it flashes, it turns into calcium fluoride. Calcium fluoride is the natural mineralized form of fluorine in the environment. So where do you find fluorine? You find it as calcium fluoride. It's a very stable compound, not very water soluble. Has some water soluble, but not very much. And it's non-toxic. So we turn it back into the natural material along with graphene. And if you had, say, 1% PFAS in there, you just have, I don't know, 1 or 2% of the metal fluoride in there. Nobody cares. Just use the graphene in concrete. Nobody's going to care. Calcium fluoride's there anyway. You can add sodium hydroxide and get sodium fluoride, and you can sell it to toothpaste producers because they put sodium fluoride for our teeth. So this is a way to deal with it. And here's the kicker, because none of this is ever going to be used if it's not good on price. So it turns out all the different ways of dealing with PFAS cost money. But this method is minus $1,900 per ton. You say, how can something be minus? I mean negative cost. Well, you sell the graphene. When you sell the graphene, you get all this excess money. Now, you say graphene runs $60,000 to $200,000 per ton, but we're not doing that. We're artificially, just on paper, lowering the price to $3,000 a ton, saying where might graphene eventually end up? The price of, say, a bulk plastic, $2,000 to $3,000 a ton. At $3,000 a ton, which is 1/20th of its current value, you're making $1,900 by doing this. So this is a great business. The government, municipalities are all going to have to start switching to carbon filters. Municipalities, like Houston. And going to start having to do this to take up the PFAS, because the restrictions on PFAS are getting harder and harder right now. They're allowing less and less PFAS in drinking water. And then what are you going to do with all this carbon? Well, you can flash it, turn it into graphene, and you have this great price advantage here that encourages you to do this and will bring business into it. So you see what you want to do. You want to take a new technology and you want to apply it in all these different areas. And then what you want to do is you've got to have it utilized, you've got to do it at a price that's going to encourage people to do it. Okay? We'll pick it up there next time. If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.